अच्छा चलिए let's start a bit. ठीक है, just a brief recap of what we were up to. ठीक है, we were talking about sigma bonds. I told you that sigma bonds is when orbitals overlap. Electron in one orbital and there's an electron in one orbital. Both atoms try to gain electrons, so the electrons kind of get stuck in the middle. So we talked about an S and S overlap, with electron density lies right in the middle. Then we talked about S and P overlap, like if you have an H atom bonding to a fluorine atom. Fluorine's orbitals are all full, except for the last one, the P orbital. Okay, except for that one, all the rest are completely full. So is this better? Sorry, just a second. Can you hear me now properly? Hello? Hanya, can you hear me? Rubab, Anna, can you hear me?
Yes, sir.
Acha. So, Anna, you can hear me properly, right?
Yes.
Acha, theek hai. So, Hanya, can you try and sit closer to the internet? Okay. Acha, so you've got a hydrogen atom with one electron, you've got a fluorine atom which has one of the orbitals and it needs one electron. So, this is fluorine's one orbital that requires an electron. This is hydrogen's atom that requires an electron. So they both try to pull each other's electrons and the electrons get stuck in the middle. So this is an s orbital overlapping with a p orbital. So the new orbital will have maximum electron density in the middle over here. And there was p and p overlap, which was that if you try to bond two fluorine atoms, all the other orbitals are full. Fluorine has a p orbital which needs an electron. So here's your p orbital around the nucleus. There's an electron buzzing around in this area, just one of them. And here's another nucleus with an electron buzzing around. That's another fluorine atom. They both try to pull each other's electrons. The electrons are stuck in the middle. So this is a p and p overlap. So we talked about sigma bonds, and we did examples of sigma bonds. That if you have a water molecule, what happens is that the oxygen needs two electrons. So what happens is that this oxygen atom over here, it has two orbitals that need one electron each. So there's the p orbital that needs one electron. So it tries to pull the hydrogen's atom towards itself, and the electrons are stuck in the middle. So that's your sigma bond. That's the two orbitals are going to merge together. ठीक है. And oxygen had another p orbital, so there was another p orbital that needed an electron. So it pulled one of the hydrogen atoms, tried to attract its electrons. The electrons got stuck over here. They started shedding electrons, and the two orbitals eventually merged with each other, and the new bonding orbital had maximum electron density right in the middle of the two nucleuses. So that was a water molecule, and we did nitrogen with fluorine. So what happened in that was that nitrogen had three orbitals that needed electrons. So there were three p orbitals, one over here, one on the y-axis, the other one on the z-axis. So fluorine, it tried to attract fluorine's electrons, so the electrons of fluorine. Fluorine had just one p orbital that needed an electron. So fluorine's only orbital that was bonding was a p orbital. So they would start overlapping and the orbitals would merge. This fluorine would try to attract nitrogen's electron. Nitrogen would attract fluorine's electron. The electrons would be stuck in the middle. And here's another overlap. So there would be three overlaps that would be happening. One nitrogen atom bonded to three fluorine atoms. So this over here was nitrogen, and it was bonded to three fluorine atoms. Now that's what a sigma bond is. We're going to now move towards, and we're going to learn what a pi bond is. Okay, so remember about pi bonds. Pi bonds is another type of bond And in this bond, the first thing is when do pi bonds happen? When are they formed? I told you that a single bond between two atoms, that's always a sigma. If you've got a double bond between two atoms, then the first one is a sigma and the next one is a pi bond. So that's your double bond. So pi bonds are only formed when you have a double bond or maybe you have a triple bond. So in a triple bond, what you have is the first one is going to be a sigma, whereas the rest of them, the other two bonds, are going to be pi bonds. So they're going to be called your pi bonds. So the first thing is that's when pi bonding happens. Uh, so we're going to do an example. Remember single bonds, they never form a pi bond. Single bonds never form a pi bond. Double bonds and triple bonds, that's where pi bonding happens. So we're going to take an oxygen molecule, an oxygen forming a double bond with another oxygen. So oxygen's electronic configuration is its outer shell electronic configuration is 2s2. 2p has 4, so 2px is also 2. You've got 2py 1 and 2pz is also 1. So anyways, oxygen needs an electron in the 2py and the 2pz. So it needs electrons in these two orbitals. And the other one is also oxygen, so it also needs electrons in these two orbitals. So both oxygens are exactly the same. So we're going to look at these two orbitals only because all the other ones are completely full. So the 2py, here's your oxygen atom. Let me draw it over here. Here's your oxygen atom. It's got a 2py orbital, an electron in this area, buzzing in this area somewhere. So there's an electron that's moving rapidly to and fro in this particular space. And there's an electron in the 2pz. So I'm calling them, this one is my 2py and the other one is my 2pz. Remember, both of these areas, they just have one electron each. And I have another oxygen atom which is going to be exactly the same. It's going to be there's going to be an electron in the 2py and there's going to be an electron in the 2pz. So remember, 2py and 2pz, both of these orbitals need an electron. So first one, let's look at the 2py. It needs an electron, so it sees the other oxygen's electron. What it would do is it's going to try and bring that electron towards itself. It would try to gain that electron. The other oxygen would do the exact similar thing. It's going to try and gain its electrons. What would eventually happen is that the two orbitals are going to merge and they would overlap because both these electrons are going to be stuck in this middle part over here because both atoms are trying to pull each other's electrons. Is this point clear? Yes or no? Is this clear? Anna, is this clear? Alicia?
Yes.
Hania, is this clear?
Yes.
So that's the first thing. Hania, is this clear?
Yes, sir.
Achha, so that's a sigma bond. A sigma bond was the electron density is right in the middle. That's the first bond that's going to be formed. So I'm going to draw the bonding orbital now, the blue one. The maximum probability of finding the electrons is now at the moment right in this middle part over here. So that becomes bigger. And the chances of the two electrons going to the other side, that diminishes. Like previously this electron was buzzing in this entire area, right? But now there would be very little chance of this electron going to the other side because it's being attracted by the other atoms. The electrons are stuck somewhere in this area. And so now the next part is what happens to these red orbitals now. The red ones are now parallel to each other. I mean, the red ones also needed electrons. But now the thing is that this electron, I mean, there's only one electron in this area, one electron in this area. I mean, this one electron is buzzing in this entire red area. This one electron is buzzing in this entire red area. Now, when orbitals become parallel, this orbital needs an electron, so it sees the other atom's electron, so it's going to try and pull its electron towards itself. And the same thing would happen that this atom over here, I mean, it had one electron in the orbital, so it needs another electron, so it's going to try and pull its electrons. So what's going to happen is that the overlapping is going to take place, but the overlapping would be above, I mean, it would be on the top and bottom area. I mean, the electrons are going to merge up, and this is the middle area is the where there's going to be a high probability of finding an electron. So the first overlapping happened right in the middle. They both tried to pull each other's electrons. The electrons got stuck in the middle over here. So one of the orbitals of this oxygen atom and one of the orbitals of this oxygen atom, they ended up forming a sigma bond, which you can see over here. Okay, let me get rid of the. So they ended up forming a sigma bond. But then the other two orbitals, they needed an electron as well. So they tried to pull each other's electrons, so the electrons got merged up. They got stuck over here and they got stuck over here. So the electron density is again maximum between the nucleus, but it's not on the axis now. The electrons are either above or below the axis. And that's your pi bond. So is this clear?
Sir, I have a question.
Yes.
If there's only one electron in an orbital, why are like
Why
both
the
of the bits joining?
Nee, what's your point? Why is there? Can you repeat?
You see how there's only one electron in an orbital?
Yeah.
So why are both the circles joining and not one like the previous one?
Nee, why are the two circles not joining up?
No, like why are the two parallel circles joining up instead of one?
I mean, these two, you're talking about these two circles.
No, the one at the bottom.
Yes, you're talking about why are they joining up?
Yeah.
I mean, the thing is that this electron over here, it's not a stationary. I mean, it's buzzing around so fast that to an outside observer, it appears that it's in both areas at the same time. Do you get my point?
Yeah, thank you.
Okay, so I mean, this electron over here as well, although there's one, but it's buzzing around. It's like it's in both places at the same time. It's like a bee that's buzzing in this area up and down. Uh, so and it's doing that so fast. It travels so quickly that it occupies both of the regions at the same time. So when they merge up, I mean, this atom, this nucleus tries to pull the electron from the other atom. This nucleus over here tries to pull the electron from this atom. The two electrons over here, I mean, one over here and one is in this area, they kind of get mixed up, and there would be a high probability of finding those electrons in these regions over here, right? So I'm going to write down the properties of pi bonds. First thing, number one is we already discussed that it's always the second, like the first bond is always a sigma bond. Like when electrons get shared, the middle part is the one that's going to be occupied first. That's your sigma bond. Uh, for pi bond, orbitals must be parallel to each other. For sigma, it was an end-to-end overlap. Like the orbitals were right next to each other, and they overlapped. One end of one orbital overlapped with the other end of the other orbital. The second property is that the electron density or the probability of finding the electron lies above and below the axis. Between the two nuclei. Because the middle part is already occupied by electrons, so that space is not available. You can't put more electrons over there. So the electron density is going to merge up above or below. So between the two nuclei, but above and below. Then another thing is that pi bonds are kind of reactive because there's a lot of negative charge that's much further away from the. I mean, this bond is hidden in the middle. Whenever something is attracted to electrons, it's going to be attracted to the pi bond. So pi bonds are reactive, and they attract things that are attracted to electrons. So there's an electron cloud that's above and that's below. So pi bonds are kind of reactive. The fourth point is rotation gets restricted because of a pi bond. Like you can't twist a pi bond because now this part of the molecule and this part of the molecule is locked in place. Like I mean you can't like if you know how to open a toffee wrapper, right? You twist it around. You can't twist this side independently. Like you can't make this independently twist around because this bond over here is not going to twist because it's locked in place with the other one. So whenever you have a double bond, rotation is no longer possible. Like in sigma bonds, rotation was possible. In sigma bonds, there was just a pair of electrons right in the middle of the two carbon atoms, right? So you could twist this side around. The bond, nothing would happen to the bond. But when you have a double bond, which you can see over here, when you have a double bond, rotation is going to be restricted because the double bond is going to lock the molecule in place. So you can't kind of twist this side independently because when you have a double bond, this is what's happening. That there's basically two orbitals that are in parallel to each other, and they're overlapping above and below the nucleus. So or the axis connecting the two nucleus. So whenever you see a double bond, there's a pi electron cloud or a pi bond. And this side cannot rotate independently because if you try to rotate or twist this, the bond is going to break. Is this point clear?
Yes, sir.
Okay, let me see if I can have a molecule that's or an image that shows this. Just a second. So here's like a better, still not a very good. So maybe this one. I mean, like, if you have a double bond over here and this atom is pointing upwards, right? I can't make it point downwards because the double bond is not going to rotate. They're locked in place. So rotation is restricted. This image might not be that clear, but it shows a pi bond. Like two orbitals parallel to each other and they're kind of overlapping above and below. Okay, the orbitals merge up, they get mixed up, the electrons they get mixed up. Now you can't rotate this side independently. Like there won't be any free rotation. That that free rotation is not going to be possible because uh, you can't sort of twist the middle part now. The middle part is locked in place. If there was no pi bond, then around this bond rotation would have been possible, which in this case it's no longer going to be possible. Like over here, if you can see if there's a single bond, like an electron density right in the middle, they're actually showing this. So if you can visualize, there's a bond, there's this carbon atom, there's this carbon atom, right? The two sides can rotate independently, just like two wheels. There's a bond in the middle, and there's a wheel on one side, there's a wheel on the other side. The two wheels can rotate independently. But if there's a double bond in the middle, then independent rotation is not possible. That is not going to happen. Is this image clear?
Yes, sir.
ठीक है बाकियों, is this clear? Anna, is this clear? Alicia, clear है?
Yes.
Yes.
Okay. So this thing, remember all these molecules when they're connected together, their bonds are kind of rotating around. But it only happens when you have single bonds, when you just have sigma bonds. Whenever you have a double bond, then this kind of rotation is simply not possible because you would have to break this overlapping. Only then that would happen. So anyways, moving on, let's try and draw another pi bond. A lot of times you'll be asked questions about this, TK, in your paper. What you just have to draw is this thing. Like you might be asked, show one pi bond, like in an ethene molecule. A lot of times they ask you about ethene molecules. So all you have to do is, like if they ask you to draw the pi bond in ethene molecules, or a pi bond in any double bond, what's basically happening is that the first bond is going to be a single bond. It's going to be a sigma bond. The electron density would be right in the middle. So use the electron density right in the middle. And then there's going to be a pi bond formed. Carbon is going to have orbitals that would be parallel to each other and they would start overlapping above and below. So that's your second pi bond that's getting formed. So a lot of times you just have to do this. Yeah, I mean, they might give you a molecule. Whenever you see a double bond, it means there's a single bond. I mean, that's there. And on top of that, the other orbitals are parallel to each other, so they are now overlapping above and below the axis. All this is all you have to do in most cases. So we're gonna try and do another one. I'm going to show you a triple bond now. Now a triple bond is like an N triple bond N2 molecule, right? That's what a triple bond is. When you have a triple bond, that means there's going to be one sigma bond, there's going to be one single bond, and there would be two pi bonds. The first one is going to be a sigma bonds. Now N, what's the electronic configuration of N? It's got 7 electrons, so that means the outer shell it's in group 5, so that means it's 2px, 2py, and there is 2pz. So there's one electron here, and one electron over here. So here's your, so it needs 3 electrons. It needs an electron in this orbital, this one, and this one in each one of them. Now, if I draw nitrogen, nitrogen will have 3 orbitals that need electrons. There's a px, let's say there's this over here is a px orbital. There's going to be a py, let's say there's an electron in the y-axis. And there's going to be a pz, which would be lying on the z-axis. So imagine an orbital on the z-axis. So what I'm going to do is I'm going to draw another one. 2 nitrogens bonding to each other. So here's my second one. The first thing is when the 2 nitrogens join up. Remember, each of the p orbital has just one electron. So let's say the px of one nitrogen atom overlaps with the px of the other nitrogen atom, and they kind of start overlapping in the middle. Right? That's your sigma bond. That's the first bond that's going to be formed. So the p is gone. It's done. It ended up forming a sigma bond. One of the nitrogen ended up forming a sigma bond with the other nitrogen atom. Now you have the py orbitals, which are now parallel to each other, or now they are parallel to each other. They also have one electron each. This has one electron. This one also has one electron. They would both try to gain each other's electrons, and eventually, what would happen is they would start to overlap above and below the axis. The electron density is going to be maximum in these areas over here. Is this clear so far?
Yes,
Yes,
sir.
sir.
I said this orbital lobe would become smaller because the electrons are now stuck in the middle, so they're not going to go or venture like really far away. The electrons are kind of stuck in the middle, so the sigma bond is going to be, it's going to have maximum electron density right in the middle. So that's one sigma bond and now one pi bond. What about the third one, which is pz? The pz would be on a different axis, which is the z axis. So here's your pz orbital. So my pz orbital is lying on a different axis, on the z axis actually. So there's my pz orbital, but they are also now this z axis is coming towards you. Okay, think of this in 3 dimensions. This pz is coming towards you. It's on the z axis. I mean, this is also the z axis. This is also z axis, but they're also parallel. So what they'll do is they'll also start to overlap in front. I mean, they would try to pull each other's electrons, and they would overlap in front and behind the molecule. So there's going to be overlapping that would be happening going on in front and behind. So there's going to be two pi bonds. One would be on the like on the y-axis. The orbitals are on the y-axis and they overlap. The other ones would be on the z-axis and they would also overlap. The first one ended up forming a sigma bond. Is this clear?
Yes, sir.
Yes.
Achha, but again, so remember that when you have a triple bond, it's going to be one sigma and two pi bonds. Remember, you won't be asked to draw this, but the knowledge is important. So I'm going to show you a triple bond, like if I can just get a better image of a triple bond pi bond. So triple bond pi bond would, what's a good image? It's probably this one, maybe this one. Let me just, this one is kind of good as well. So if you look at this one, it's nitrogens, each one of the p orbital was empty. They were trying to pull electrons, right? So the first thing that would happen is when they bond with each other, the very first thing is these p orbitals are going to merge up. I mean, they're going to try and pull each other's electrons. So they would merge up. So there's going to be right in the middle, right in the center, there's going to be a p orbital. A p and p overlap would be happening. So there's a sigma bond that's hidden between this. And then from the top, right from the top, there's going to be, if I change, these two p orbitals would start to overlap. Like this orbital is parallel to this orbital, so that's your pi bond that would be formed. And then the green ones would also start to overlap. The green ones are on the z-axis; they're also parallel to each other, so they're going to overlap in front and behind the atom. So they're going to be two pi bonds, one overlapping above and below, the other one overlapping in front and behind. Uh, like this one. One second. Right, so you have the p and p orbitals, they overlap right in the middle. And then one of the p orbital overlaps with one of the other p orbitals and they start to overlap above and below. This one overlaps in front and one of them overlaps behind. So just as I've drawn over here, you're getting two pi bonds and one sigma bonds. Is this clear?
Yes, sir.
Okay, so just remember the knowledge is important. The drawing part is going to be simple. In your exam, if you're being asked, like if they give you an HCN molecule and they ask you draw the sigma bond or draw the pi bond, what you're just going to do is it's going to be H with a C. The first bond is going to be it's going to be in a triple bond. The first bond is always a sigma bond, so the electrons are going to be right in the middle. The second bond is going to be a pi bond, so that means orbitals would be parallel to each other and they would be overlapping above and below. And if they ask you, there's going to be two pi bonds. The third one would be on the z-axis. So the z-axis one would be, it's going to be the same, except that the orbitals would overlap above, not above, but in front and behind the atom. So they too would overlap, but the overlapping would happen in front and behind. So you'll be asked about drawing just one pi bond or one sigma bond, that's it. But remember this, the important thing is that molecular rotation is now restricted. Independent rotation is not possible once you have a pi bond. Electron density lies above and below the axis. Always remember that whenever you have a single bond, it's always a sigma bond. The first one is always a sigma bond. And the second, if there's a double bond, if there's a triple bond, those are going to be your pi bonds, right? So we're going to talk about another thing which is very similar, and that's your hybridization of carbon atoms. Okay, it's again a very small topic, but it requires a bit of understanding. So we're going to learn about hybridization of carbon. What is hybridization? Hybridization is, it's the mixing of orbitals to form new hybrid orbitals. In simple words, in simple terms, what it means is orbitals that they just change shape when they bond. And we did see a fair bit of hybridization. Orbitals change shape. We did learn this. Like for example, if you have a p orbital that's overlapping with a p orbital, the orbitals are going to merge and they're going to change shape. Okay, so this was happening everywhere. Like even in the first one that we drew, like in the S and S overlap. Previously, if there was an independent hydrogen atom, the electron was like in a spherical region around the nucleus. This electron was also in a spherical region around the nucleus, but the electrons kind of got together, they merged up, and they ended up forming a sigma bond, which is both orbitals. They eventually change shape. They're no longer spherical because they've mixed up now. So hybridization simply means that orbitals are going to change shape when they bond because of the attraction and the repulsion of other atoms. So carbon has 4 electrons in its outer shell. I mean, its outer shell is 2s, 2px, 2py, and 2pz. So there's 1 electron each. Now, carbon needs 4 electrons. I mean, you always knew that carbon makes 4 bonds. Carbon is in group 4. It has 4 electrons in its outer shell. It needs an electron in this 2s orbital. It needs an electron in the 2px. The 2py is also empty, and the 2pz is also empty. So it needs 4 electrons. So what happens is, remember, S is spherical. Like the S orbital, the electron is going to be, it's going to be in a spherical region around the nucleus. So the electron, I mean that's the first one, is buzzing in this spherical region. Similarly, the 2px, 2py, and 2pz. So these are your orbitals. The 2px is going to be on the x-axis, so there's going to be an electron that would be buzzing in this area. There would be an electron in the 2py axis. So an electron would be buzzing in this area. And there's going to be one of the electrons is going to be in the 2p z-axis. So there's going to be one electron in this area. So carbon has a total of 4 electrons. All these electrons are buzzing in their own areas. Like you had a spherical area where the electron is buzzing around. You have a p orbital, electron is buzzing in this area. There's an electron buzzing in this area. There's an electron buzzing in the y-axis. So each electron is roaming around in its own space. What happens when carbon bonds? Now remember, carbon has 4 electrons. What happens is, here are 4 hydrogens that are coming, and each one of the hydrogen needs an electron. So what they're going to do is, like, there are 4 electrons that are buzzing around carbon, right? Each occupying a very specific shape, existing in a very specific shape around the nucleus. So you've got 4 hydrogen atoms, and all of them, they need 1 electron. So carbon has 4 electrons in the middle, right? All buzzing around. It's like 4 flies that are flying around the carbon atom. But now all of a sudden what happens is one of that fly gets attracted to one of the hydrogen atoms. The other one gets attracted to the other hydrogen atom. The third one gets attracted to the third hydrogen atom. And the fourth one is being pulled towards the fourth hydrogen atom. Is this idea clear so far?
Yes, sir.
Nabil, Nabila, is this clear? Hania, Bob, is this clear?
Yes, sir. Yes, sir.
I said, so when carbon was all alone, all these flies, they had their own spaces. They were just buzzing around in those spaces. Now when these hydrogen atoms came along, their nucleuses, they started attracting these electrons, so they all went in their different directions. So the shape of the orbital would also change. Like, there is no longer a spherical orbital. The electron is not buzzing around in a spherical orbital anymore. The carbon is in the center. The electron is somewhere buzzing. It's being pulled by the hydrogen at the top, right? There's an electron that's buzzing in this area now. There's an electron that's getting pulled over here. There's an electron that's getting pulled in this direction. So you've got 4 hydrogen atoms. Now the shape of the orbitals are going to change. You still have 4 electrons. There's 1 electron going in that direction, 1 electron going in this direction, the third electron going in this direction, and the fourth electron being pulled in this direction. Now the only thing is, you can't call the orbital S now, because S used to be spherical. Now it's not spherical. Like, the electron that was buzzing around in a spherical region has all of a sudden gotten pulled by the hydrogen atom. It's no longer a spherical region. It's not occupying a spherical region anymore. Same is the case with px. Like, a hydrogen atom came along, the electron was buzzing in this green area over here, but all of a sudden all the electron gets attracted to the hydrogen atom. So it's no longer buzzing in a p orbital. And same goes for py and pz. They're now non-existent. You've got 4 other spaces now. It's still 4 electrons, but you have to give them some names. The space needs to be given some name. The orbital needs to be given some name. So you start calling them sp3 hybrid orbitals, because during bonding their shape changed. So instead of calling them a spherical orbital or a double shaped px orbital, py orbital, or pz orbital, what you do is, because during bonding the electrons got pulled in different directions by different atoms, you start calling them sp3 hybrid orbitals. And all 4 are now identical. So this is what has happened. Carbon bonds with 4 atoms, and during bonding the shape of the orbitals, it changes, because the electrons get pulled in different directions. And if the shape changes, the name of the orbital must change also, because now there is no spherical, there is no double shaped. 1 electron getting pulled in this direction, 1 electron getting pulled in this direction. All 4 look identical, so you give all 4 of them the same name, and you start calling them sp3. What sp3 just stands for is that there's 1s and 3p. All of them, they ended up changing shape. Is this idea clear?
Yes, sir.
ठीक है बाकियों को इज दिस क्लियर आयशा इज दिस क्लियर Anna Alicia Abdullah clear है Rubab
Yes, sir.
so that's it that's hybridization that the orbitals are given different names because during bonding the electrons are now somewhere else they're no longer in a spherical region they're no longer in a double shaped region all of them they get pulled in different directions by different atoms so which is why you give them a new name which is sp3 hybrid orbitals. So okay, let's continue with sp3 hybridization. One second.
Sir,
Yes.
isn't the electron configuration S2p2 in carbon?
Which one? I said that's S2p2. Yes, it is S2p2. I'll come to that. It's what happens during bonding is like it's S2p2, right? Uh, carbon's outer shell. It's S2 and P2 means the p subshell has three orbitals, right? So there's 1, 1, and 0. I mean, if you according to the off-off principle, this is the electronic configuration you're going to get. Actually, it's going to be 2s2, 2px1, 2py1, and 2pz1. What happens during bonding is this is what happens. Like it has four electrons. Two of the electrons are together at the moment, right? But what happens? Like one hydrogen atom pulls the electron in one direction, the other one pulls the atom in the electron in the other direction, the third one in a different direction, the fourth in a different direction. So do you think all the electrons are going to stick together? Like instead, all the electrons they get spread out in different direction. One gets pulled in this direction, so this is what you're imagining that the electrons are no longer going to be together, even though initially the s orbital had two electrons. But because they're getting pulled, like imagine there are two electrons in the s. One electron gets pulled in this direction, the other one gets pulled in this direction. So now they're kind of in separate orbitals. Is this idea clear?
Yes, sir. Thank you.
Okay, so remember this, okay, during bonding, the electrons kind of get distributed in the outer shell. Like if something has six electrons or four electrons or three electrons, then because all the atoms are pulling the electrons in different directions, so they kind of occupy separate orbitals. Okay, if there is room. So instead of two electrons in the s, there's going to be just one electron, and one electron would be in a separate orbital. So okay, let's continue tomorrow with hybridization. Okay, everyone, take care.
Right, sir. Thank you,
Allah
sir.
Hafiz. Thank you.
Okay.
Allah Hafiz.
Allah Hafiz.